Welcome to Numerical Methods for Scientists and Engineers with Pseudocodes. Video 11. Classic Gram-Schmidt Process. The Gram-Schmidt process is an algorithm for orthogonalizing a set of vectors in an inner product space, typically Euclidean space. The goal of the process is to take a set of linearly independent vectors and turn them into a set of orthogonal vectors, which can then be used for various purposes, including QR decomposition. The QR decomposition is directly related to Gram-Schmidt process. Any application of QR decomposition is an application of Gram-Schmidt, which is used to form Q and R. The method is used in several applications, especially in solving systems of linear equations, eigenvalue problems, and least squares approximation. Consider a positive definite and symmetrical tridiagonal system. The Gram-Schmidt QR decomposition will be described here. We begin with n independent basis vectors, T1 through Tn, i.e., the column vectors of a matrix as illustrated below. The goal of this process is to produce n orthonormal vectors Q1 through Qn, i.e., the column vectors of an orthogonal matrix Q. We start with Ti and subtract off its projections onto the previous Q's to find the orthonormal Qi, and then divide by the length of the vector U to obtain a unit vector as follows. Here, our JK denotes the inner product defined as the inner product of TK and QJ, defined as our JK, is used in constructing the upper triangular matrix R as follows. The entries below diagonal are 0 since the inner product of TK with QJ is 0 for j greater than k. The algorithm is applied as follows. Find the unit vector. Find projections. In this algorithm, the matrix R is constructed row by row, whereas in the modified Gram-Schmidt algorithm, this is done column by column. The advantages of the Gram-Schmidt method are: the method is simple and easy to implement. It is not an iterative method, i.e., the Q and R matrices are found in n steps. Unlike the QR iteration method, a complete Q and R decomposition is performed. Hence, the method can be employed to solve a linear system as well. The disadvantages of the method are: the process is inherently numerically unstable. It is sensitive to round-off errors. As a result, for very large matrices, the orthogonality can be partially or completely lost, requiring the computation of QIs to the machine epsilon level. It gives only the eigenvalues. Another method should be utilized if eigenvectors are also needed. Let us consider the following positive definite and symmetric tridiagonal matrix. We want to apply the Gram-Schmidt process to obtain the QR decomposition of the given tridiagonal matrix. The given matrix is: we extract 4 column vectors, which are independent basis vectors, and label them as T1, T2, T3, and T4. We set U1 to T1. We calculate its magnitude, which is R, 1, 1. And then, we find the first orthonormal vector Q1 by setting it to the normalized vector U1. Next, we compute projections of Q1 onto the existing basis vectors T2, T3, and T4. In the following steps, we subtract the projections from the basis vector to obtain an orthogonal vector. For the vector T2, we obtain U2 as follows. Its magnitude of U2, which is our 2, 2, is found, and we normalize U2 to obtain orthonormal vector Q2. Next, we compute projections of Q2 onto the basis vectors T3 and T4. We subtract the projections of Q1 and Q2 from the basis vector T3 to obtain U3. Its magnitude R 3, 3 is found, and the vector U3 is normalized to obtain Q3. Next, we compute projections of Q3 onto the basis vector T4. Finally, we subtract the projections of Q1, Q2, and Q3 from the basis vector T4, which gives the vector U4. Its magnitude R 4, 4 is obtained as. The orthogonal vector Q4 is found by setting it to the unit vector of U4. The columns of matrix Q are the orthonormal vectors. The matrix R contains the computed values of Rij as follows. That is all for now. See you next time with another topic. Bye.